So good morning, everyone. Welcome to the GISS Sea Level Rise Seminar. And we're very glad to have Dr. Ching-Yao Lai. She's an assistant professor of geophysics in the Dorr School of Sustainability at Stanford University. And her group focuses on attacking fundamental questions in ice dynamics, geophysics, and fluid dynamics by integrating mathematical and machine learned models so as to assess world challenges such as advancing scientific knowledge of ice dynamics under climate change. Prior to her current position, Dr. Lai was an assistant professor of geophysics and atmosphere and ocean sciences at Princeton University and affiliated faculty there in the program in statistics and machine learning. Dr. Lai earned her undergraduate degree in physics from National Taiwan University and her PhD in mechanical and aerospace engineering from Princeton University, and conducted research as a postdoctoral fellow at the Lamont Doherty Earth Observatory of Columbia University. So today, Professor Lai will be speaking on the topic, changing ice in a warming climate, data-driven approach. So, welcome.
Yeah. Okay, yeah, thank you, Patrick, for a very nice introduction. So yeah, I was a postdoc at Lamont, I guess from 2018.
This meeting is being recorded.
Oh, sure. Yeah, from 2018 until during the pandemic. So it's nice to see many familiar faces in this Zoom call. So as Patrick mentioned, I study the dynamics of ice. Ice dynamics plays an important role in our climate systems. And something that's quite interesting about ice is that it's a fluid, but it is barely a fluid. You can see ice cracking and behaves like a solid. So I hope I can convince you today that ice is a fascinating topic, and there are lots of emergent opportunities at the intersection between data models and data-driven approaches. Okay. And I will spend some time going through the basics of ice dynamics. So many of you are expert of sea levels, and please bear with me. So this is Antarctica. It's a giant piece of ice sitting on top of bedrock. And glaciers are ice that flows viscously downslope into the ocean. So currently there are two ice sheets, the Antarctica and Greenland ice sheets. As climate warms, the melting of the two ice sheets, along with the melting of the mountain glaciers and the thermal expansion of ocean contribute to the global mean sea level rise. And this is the prediction of the global mean sea level rise in the next 100 years from a recent IPCC report. So in the high emission scenarios, we'll likely get a meter of global sea level rise by 2100. This prediction does not include ice sheet instability processes, which are highly uncertain. If we consider these deeply uncertain instability processes, such as the marine ice sheet instability, current simulations predict another extra meter of sea level rise, and that's shown by this dash curve. So a common goal of ice sheet modelers around the globe is to understand these deeply uncertain processes which can impact the future mass loss of ice sheets. And a big question is, how does ice sheet respond to climate change? Although continuous progress has been made to large-scale ice sheet models, there are still many processes that need to be better understood before coupling them with the continental ice sheet model. And those will be the focus of today's talk. So ice flow is driven by gravitational spreading. And here is a velocity map of ice flows. Purple is the fastest flowing ice, and green, orange are the slower ice flowing at a slower speed. So the flow velocity is sensitive to the boundary conditions at the bottom of the ice sheets. To the first order, the blue and purple areas flow the fastest because ice is spreading over oceans, and we call it ice shelves. In contrast, the velocity of ice sheet is slow, and as shown in this orange and green area, because they lie above the bedrock, which provide frictions to slow the ice flow. And note that this cartoon is exaggerated in the vertical scales. The actual exponential between the thickness and the length of the ice sheet is about 1/1000. So this is a very thin layer of flowing ice. So ice is supplied by snow accumulation, but then removed at the ice shelves by either melting or calving of icebergs. The ice loss through these two mechanisms has been estimated by Rigner et al. However, there are many unknowns that are still active area of research, such as what's the physics of calving. There are many calving laws that are empirical, and we do not have a universal calving law that describe both the calving in Greenland and Antarctica. And second, how does the ice respond? How does the ice loss respond to a warming climate? We know that ocean warming can melt the ice from the bottom, while atmosphere warming can create melt ponds that have a profound impact on the stability of ice shelves, which I will talk more about later. And finally, how does the loss of ice shelves impact the flow of ice sheets? So if the collapse of ice shelves do not change the flow of ice sheets, then it's not that important. So in the first part of the talk, I will partially address these three questions. And this is today's talk outline. There are two different stories I would like to talk about, ice cracks and ice flows. So the first story is about how ice fractures and how it removes ice from ice shelves. And the second story is about the rheology of ice, which is one of the fundamental properties that governs the dynamics of ice flows. Okay, let's get started. So here, this is a iceberg calving event. You can see a crack propagating through the brown ice shelves in about 6 days, and then cause the breakup of an iceberg about 20 times larger than the size of Manhattan. Note that iceberg calving occurs naturally without climate change, but atmospheric warming can enhance this fracturing process. So these are just examples of the regular patterns of cracks. This is a satellite image of the Thwaites Glacier in 1996, which is heavily fractured. And you can see most of the ice shelf has broken into icebergs between 1996 and 2016. So here's a cross-sectional view of the ice shelf with surface fractures. As climate warms, the meltwater can fill the fracture, and the heavy water enhance vertical fracture propagation by a similar process as hydrofracturing. So when iceberg calving occurs, the front of the ice shelf retreat. And strikingly, in 2022, almost the entire Larsen B Ice Shelf collapsed within a few weeks. This rapid disintegration of the ice shelf area is widely believed to be caused by this climate-induced hydrofracturing. Most importantly, there was direct observational evidence that the upstream glacier can accelerate after the collapse of ice shelf, because ice shelf plays a critical role in holding back the upstream glaciers. The loss of ice shelf can trigger faster ice flows and then result in faster sea level rise. So in fact, ice sheet modelers had shown that by including a simple hydrofracture as well as cliff failure mechanism that will result in a much higher sea level rise predictions. The problem is how to accurately include hydrofracture physics in ice sheet model is still an open question, and it's a key uncertainty in quantifying the future of ice loss. So the question I'd like to address in the first part of the talk is, will hydrofracture significantly impact the flow of the Antarctic ice sheet? To address this question, there are three components that are critical to consider. First, the existence of meltwater is essential for triggering hydrofracturing. And we also need to know the areas, if collapse, would have an impact on the upstream glacier, meaning the areas that provide buttressing stresses to support the upstream glaciers. Finally, we need to know the regions of ice shelves that would that's vulnerable to fracturing. So the tricky thing is in general, ice tend to be most vulnerable to hydrofracture near the front of the ice shelves because this is where ice gets stretched the fastest. On the other hand, farther back from the front are the areas that actually provide strong buttressing stresses to support the ice sheet. And loss of these buttressing areas will significantly accelerate the flow of the upstream ice sheet. So the question we want to ask is whether this fracturing area also provide buttressing stresses. In other words, are there any overlap between this red fracturing and the green buttress regions? So to answer the question, we want to first understand where do fractures form and what are the areas that's vulnerable to hydrofracture if the crack is filled with meltwater. Finally, are the regions vulnerable to hydrofracture important? In other words, are there any overlap between the hydrofracturing and the buttressing regions? Okay, so the fracture depth can be determined by a few things. First, this is the cross-sectional view of an ice shelf and a surface crack. The existence of extensional stresses result from the background gravitational spreading, and that can help open the crack. However, we have the overburden stresses of ice resulting from the weight of the ice itself, and that can resist the crack to grow. If we have meltwater filling the crack, because water is heavier than ice, so now there are additional hydrostatic stresses of water that can help opening the crack. So here we will use the classical linear elastic fracture mechanics approach to quantify 3 different outcomes of the fractures. Either we will have no crack, or the crack can exist with a stable depth, or the fracture can be unstable, meaning that the crack can just keep growing until it breaks the entire ice thickness. So what do we mean when we say stable and unstable? An easy way to quantify the stability of the crack is calculating the stress intensity factor as a function of the depth of the fracture. So stress intensity factor is related to how fast the elastic strain energy released as the crack propagates. And this black curve is the stress intensity factor calculated from the contribution of the extensional stress and the overburden stresses of ice. So crack can only grow if the black line is above the red line, which is the fracture toughness, and it's a property related to the energy required to break the ice. So for a smaller crack depth, the extensional stress dominant, and that can destabilize the crack. But for a larger crack, the effect of the overburden stresses come in, and then that can stabilize the fracture. So in this scenario, this is the final stable crack, stable depth for the fracture. However, when we start to add water in the fracture, if there's sufficient water, the fracture now can just have one unstable solution, meaning that as long as we have an initial flaw that's filled with water, the flaw will just keep growing until you break the entire ice thickness. So this is what we mean by unstable fracture, and this unstable behavior occurs when we have this pre-existing flaws in the ice that's larger than the initial flaw size. Okay, so now it's useful to quantify our result by non-dimensionalize our equations. We obtain 2 different non-dimensional parameters that determine the crack stability. The dimensionless stress, which is the extensional stress rescaled by the overburden stresses of ice, and we have the dimensionless toughness. And we plot the stability of the crack as a function of the dimensionless stress and the dimensionless toughness for a different amount of water in a fracture. So here, when we do not have water in a crack, the crack is either in a stable crack regime or there can be no cracks. However, the crack can be fully destabilized when the crack is fully filled with water. And now we focus on the simplest case when there is no water in the fracture. So depending on the value of the 2 fundamental parameters, which depend on the stress, the thickness, and the toughness, we have 3 different outcomes of the fracture. there can be no crack. The crack can be stable. It can be unstable. And now we want to compare with observations. So the Earth is like a natural laboratory, and we have observation of velocity of the ice that can be used to calculate strain rate. We have the thickness of ice available over the entire Antarctica. And the viscosity parameter, which I will mention in the second part of the talk, can, to the first order, be estimated by the temperature of the ice. And the fracture toughness is a material property that can be measured in the laboratory. But we also need to know where cracks form. And here I train a deep convolutional neural network to learn the patterns of fractures satellite images. For example, on the left is the input satellite image. You can see the fractures in many, many places. And the right is the prediction of the neural network. So here the grayscale is the likelihood that the pixel contains a fracture. And you can see the white patterns capture the fracture locations. So next, I applied this trained neural network to produce a map of fracture locations across the ice shelves. Here, roughly 2 million points out of a total of 80 million pixels of the ice shelf areas are identified as fractures, and it's marked in white color here. So here's another close view example. You can see the neural network do a pretty good job identifying the fracture patterns. And now we can use this fracture location as an observational benchmark to compare with our theoretical predictions. So we recall the prediction of fracture stability. Here, this gray triangle region is where we expect to see fractures. And now we plot the observational result. There are about 2 million points here. Each point represents the parameters calculated from the strain rate, the thickness, the toughness, and the fracture locations. We found that the majority of this point where the neural network detects fractures lies in this gray area and agrees with the physical regions we predict without any fitting parameters. In addition, from scaling argument, we obtained a simple power law for a simple expression for this no fracture to stable fracture transition boundary, and that agrees very well with our numerical solution. So the benefit of this simpler expression is that it can potentially be directly used in a large-scale ice sheet model without expensive computation of the linear elastic fracture mechanics. And so last year, there's a paper on the cryosphere paper about a quite exciting result that report the analytical value for this stable crack to unstable crack transition boundary, and that agrees quite well with my numerical solution. Okay, so from this approach, this allows us to compare a physics-based model with observations over the entire Antarctic ice shelves. This will be otherwise quite difficult without the machine learning technique. So far we were looking at dry cracks. A natural question is what will happen if now we add water into the crack as climate warms. We have previously shown that the crack stability switches from stable to unstable when we add water into the fractures. Here we upscale our analysis to the entire Antarctica, and in the extreme case, when meltwater fully filled the fractures all over ice shelves, here we find that the majority of the ice shelves are under the physical conditions that's vulnerable to the unstable hydrofracturing, and this is indicated by the red areas. On the other hand, the green areas are places with insufficient stresses, and these are the areas where we need a lot of large initial pre-existing cracks to destabilize hydrofractures. But in these green areas, we do not have, the stresses are pretty small, so we do not have large initial flaws. Therefore, the green areas is pretty strong and resilient to hydrofracture. So now we compare this map with distribution of meltwater observed from satellite image. Here, the blue spots are the places covered with melt ponds, in Georgia 6 ice shelf and the Emery ice shelves, you can see the meltwater mostly lie in the green resilient areas. However, in the warming climate, if the meltwater moves from the green resilient area into the red vulnerable areas, we expect hydrofracture to occur. So now, are these red vulnerable areas to hydrofracture important for ice sheets? So previously, first did this numerical experiment to show that the removal of the yellow part of the ice shelf can significantly accelerate the flow across the grounding line from the ice sheet. However, the collapse of just the blue regime does not impact the flowing ice sheet. So here we compare our vulnerability map with first result, where the blue area denote the passive ice, shelf ice that does not impact the ice sheet if collapsed. And we find out that the majority of the red area is beyond the unimportant blue regimes. Therefore, a large portion of the ice shelf is both vulnerable to hydrofracture and provide significant buttressing. So we find that the overlap between the buttressing and the vulnerable area covers about 60% of the total ice shelf area. Therefore, if hydrofracture triggers ice shelf collapse, our result indicate that hydrofracture can reduce the ice shelf buttressing and impact the flow of ice sheets. Okay, so I guess this is a short summary for the first story. We developed a fracture stability phase diagram. We use deep learning to identify fracture locations, and our results indicate that there are large portions of Antarctic ice shelf area that both provide buttressing and will be vulnerable to hydrofracture. So for future work, we would like to understand, how does ice-ocean interactions affect the ice shelf cracks. So here I'm just talking about the surface fractures. However, we know that the cracks can exist at the base of ice shelf, and that's quite sensitive to various ice-ocean interaction processes. And I'm also quite interested in the impact of different rheology on the stability of fracture. The ice here we treat it as a brittle elastic material, but in reality it can flow as a fluid, and that can affect the stability analysis. And finally, something I'm quite interested in is how here we look at a extreme scenario when there are already melt ponds everywhere on ice shelves. However, an important question is how fast will melt pond be produced on the ice shelf and then be coupled with this hydrofracture process. And to answer that question, we need to couple this vulnerability map with a climate model. Okay, so now I will, so far, I've been focusing on brittle processes when we have fast fracture propagation on ice shelves, and ice is just treated as a solid. Now I'll move on to the second part of the talk about ice flows. So we know that when we try to predict the dynamics of ice shelves, we have to solve a system of equations that include the conservation of mass, the conservation of momentum. In this case, it's just a balance between the gravitational driving stress with the viscous deformation in ice. Importantly, we also need to specify the rheology of ice, which dictate the relationship between the stress and strain rate. So when we write down the equations for ice, we start with the Navier-Stokes equation. And if we look at we can estimate the terms, the magnitude of the terms in the equation, and find out that based on the velocity and the length scale of ice shelves, the inertial terms is much smaller than the viscous terms. So in the ice dynamics modeling, we can completely ignore the inertial term and obtain the Stokes equation. Another nice thing about ice shelves is that the horizontal length scale is much larger than the thickness length scale. So we can integrate our Stokes equation vertically and obtain Michael obtained this simple set of partial differential equation that describe the ice dynamics, and it's called the shallow shelf approximation. So if you look at this set of PDEs, it involves velocities, densities, and thickness, and these are measurable quantities. However, it also involves the effective viscosity, and that's a quantity that's impossible to measure at a continental scale. So when I say effective viscosity, I simply meant this coefficient between the deviatoric stress tensor and a strain rate tensor. For ocean and atmosphere, water is Newtonian, so viscosity is constant. For ice, it's considered as a non-Newtonian fluid, so the viscosity is not a constant. It can depend on strain rate. And as we know, the knowledge of ice viscosity is critical for the prediction of ice dynamics. So conventionally, the widely used Glenn-Spall law in ice sheet model is based on laboratory measurement, which demonstrate that the strain rate increase with stress as a power law. And here the fitted exponent of the power law is about 3. And this prefactor depends on temperature. However, we know that the rheology of the glacial ice in the realistic environment can be much more complicated. The prefactor can depend on pressure, impurities, grain size, and this effect can be coupled, and it can be difficult to untangle the effect of each. Additionally, the realistic parameter range on ice shelves, the strain rate is about, it can be as low as 10 to the minus 11, 1 over a second. And this is a regime that's pretty difficult to reproduce in the laboratory. So the rheology of glacial ice has been widely debated for the past 60 years. And here we want to explore, without assuming a power law rheology model, can we learn the correct viscosity model from real world data? So fortunately, in the past decades, remote sensing technique made continent-wide velocity and thickness data widely available. Our goal is to find the viscosity such that along with the observed velocity and thickness data satisfy the equations. And here I'm going to briefly introduce a technique that we use to do this inversion, the neural network that's informed by physics. So just so that everyone is on the same page, what is a neural network? Neural network is a model of some output parameter as a function of input. And here I'm just mainly focused on a fully connected multi-layer neural network. So when we pass information from the input parameter to the first neuron, what we do is simply multiply the input with some weight and plus a bias. And then we apply some nonlinear function called the activation function. So common choice of the activation functions are hyperbolic tangent or sines. This is the expression of the output of the neuron in the first hidden layer. And then we can do the same operation repeatedly, then sum the output of the neurons from the first layer together. And then we can repeat the operations and obtain the output of the neuron in the second hidden layer that looks like this. So eventually, we can simply write down an analytical expression of the output as a function of input. We have this nasty expression. But what's important here is that this expression contains lots of constant that are fitting parameters. So the weight and biases are parameters that are that's to be determined. And it has been shown that neural network structure has lots of nice property. Neural network can be used to approximate high dimensional functions. A simple way to think about it is a single layer neural network. If we use sine as an activation function, it's actually pretty similar to Fourier series, where the weight connecting the input to the neurons represent the frequency of the signs, and the weight connecting the neuron to the output represent the amplitude of the signals. Okay, so we know that neural network can be used to fit data. Here we have is an example of some data point of U as a function of X. Throughout the training iterations, the neural network will find the weight and biases that best minimize the cost function. And with the optimized weight and biases, the prediction will passes through and interpolate the data points. Again, the prediction of a neural network is a continuous function of the input parameter. And you can imagine that if the data are sparse and noisy, then the interpolation will overfit the noise in the data. And this is where imposing physics constraint is really important. So now we suppose that the output of a neural network obeys some PDEs. We can substitute the neural network prediction into the equations and calculate these derivatives using automatic differentiation. So the equation residue should be 0 if the output strictly satisfy the equations. And now in the cost function, we include both the data as well as the equations. So throughout the training iterations, the neural network try to find the weight and biases that minimize the loss, so that the prediction of a neural network not only satisfy the equations, but also are consistent with the observations. So a neural network that minimizes the cost function is an approximate solution of the differential equation. All right, so in summary, the neural network informed by physics is a class of differential equation numerical solver. It utilized neural network's representation power as a universal function approximator, and the derivatives of the output with respect to the input can be calculated exactly and easily because we actually have an explicit expression of the output with respect to the input. So here is the detailed setting of our neural network. We train a neural network to learn the velocity and the thickness field that closely approximate the observed velocity and thickness data. Then we evaluate how well the neural network predictions satisfy the shallow shelf equations. Then the mismatch between the neural network predictions with the observations and the equations will be penalized and used to update the neural network parameters. So throughout these training iterations, the neural network will find the velocity, the thickness, and the viscosity fields that are consistent with both the observations and our physics equations. So here we first test a framework with synthetic data. We show that for a idealized ice shelf, we can, using the velocity and the thickness as training data, we can use this framework to invert for the effective ice viscosity without any training data from the viscosity. And this inferred viscosity agrees well with the ground truth viscosity field. So now we move on to using the real data from of velocity and thickness. First, we confirm that the neural network can precisely fit the observed velocity and thickness. Then by solving the shallow shelf equations, the neural network can predict the ice effective viscosity, which we cannot directly measure in the field. And because we don't have any training data for viscosity, the prediction of this effective viscosity is only possible because we include the physics equations during the neural network training. So the outcome of this approach is this two-dimensional field of ice effective viscosity. And if we substitute this back into the equations, we find that the residues are about 2 orders of magnitude smaller than the terms in the equation. So the errors of this inversion are small and quantifiable. And now there's a lot we can do with this viscosity. We can test the commonly assumed power law rheology in ice sheet model. So we start with, we have the strain rate that's available from velocity data. And then from the viscosity, we can calculate the glaciological stress with the strain rate using the constitutive law. And now we focus on the Emery Ice Shelf. So we look at the rheology along a flow line where that passes through the upstream region where the ice is under compression, and then into an extensional area where ice is is being stretched. So when we calculate the stress and the strain rate along this flow line, this is what we get. So if we just focus on the upstream areas where ice is under compression, we see that the stress and strain rate precisely agrees well with a power law with a fitted exponent that's closer to 1. And we can, do this same experiment. We can perturb the flow line a little bit and see a consistent power law in our nearby regions. However, if we now move down to the extensional zone, we see that it's unclear that a power law model is a good, well describe our stress and strain rate relationship. And we're still trying to understand what caused this kind of behavior. So if we look at this entire flow line, we see a clear difference between the rheology in the compression zone and the extensional zone. And we can do this for a few other ice shelves where we look at the compressional zone, and then we consistently find that the stress and strain rate relationship exhibit power law relationship, but with a power law exponent that varies between 1 to 3. And we can do the same trick. So we perturb the location a little bit and see robust reproducible result. So yeah, there's still much more to learn from the data. Here we show that in the compression zone, the viscosity obeys power law, but with a exponent that's smaller than 3, which is widely used in ice sheet model. And previous lab experiments showed that different creep mechanisms could lead to the stress exponent that's smaller than 3. So here we show field evidence of this small stress exponent of Antarctic ice shelves. On the other hand, the physical basis for the rheology in the extensional zone remains an open question. So one thing that's worth thinking about is the fact that in the extensional zone, we have a lot of cracks, like what we talked about in the first part of the talk. So it's possible that some physics can be violated with the existence of these cracks. And we're still working on understanding the rheology in these extensional regions. So in summary, we show evidence that the exponent can be smaller than 3 in the compressive zones of ice shelves. And this is a first attempt to use neural network informed by physics to infer viscosity structure of ice. And for ongoing work, we're trying to understand the fundamental cause for the crazy rheology behavior in the extensional zones. And we're also trying to understand the impact of a smaller stress exponent on ice flow simulations. Okay, so I want to take a step back to sum up. In the past few decades, continent-wide observations such as ice velocity, basal topography, thickness, and satellite imageries becomes available. At the same time, we have physics models that range from first principle equations like the Stokes equations to sophisticated models such as the subglacial hydrology models. Climate science is very challenging because we have lots of data, we have lots of equations, but we actually don't quite have enough of either. Very often the models include so many free parameters that you wish you could have more measurement to constrain the models. And very often observationalists want the models to include some more sophisticated considerations to capture their observations. What I'm really excited about is the fact that there has been more and more success stories of the use of data-driven methods to tackle questions in climate science and address the gap between observations and models. And this is a thriving field with many enthusiastic and bright minds from both the climate science and computer science communities. So I want to emphasize that, in the end, the data-driven findings are all empirical. And moving forward, I think it's important to sit down and think hard about these data-driven predictions in order to understand the result. This is the part that really require human brain and scientists. So the point of data-driven method is not to throw everything to a machine and stop thinking. Instead, I believe a data-driven world correspond to higher demands for deep thinking to rationalize the result. Okay. And finally, I want to thank my colleagues. So the first part of the story is a fun collaboration with people from engineering, earth science, and computer science. Johnny Kingslake and Martin Waring are the glaciologist, and Mel here is a climate modeler. Poshan is a researcher at the Google research team. And the second story is done in my group, mostly by my postdoc Yang Ji, who has been truly tremendous. This project would not be possible without his inspiration. Okay, so I want to end by saying that we are looking for new members to join our group. We're broadly interested in developing mathematical models to understand ice processes, and at the same time, leveraging deep learning technique to accelerate discoveries from cryosphere data set. So feel free to get in touch and send me your CV if you're interested. Okay, I'll stop here and take any questions. Go
Thanks
back
a
to
lot.
the summary slides. Yeah.
Do we have any?
Can I really see Jeff has a hand up?
Yes.
Right. Have you considered using the fracture detection to determine whether you could have surface rivers rather than direct hydrofracture? So, like the Manson and Georgia 6 Ice Shelf, and to a certain extent, Amory, the runoff from melt is through rivers rather than through hydrofracture.
I couldn't hear very well, but okay, sorry, can you repeat it, the last part again? I think maybe this is the sound of my, couldn't hear very well.
So you could use a fracture detection for to detect rivers rather than so ice shelf rivers rather than hydrofracture directly. So a lot of ice shelves have runoff of melt through the rivers rather than causing hydrofracture.
Only a few ice shelves have runoff.
So you're asking whether we have tried using detecting rivers on ice shelves?
Yes.
Right. So, I think, well, for, not for Antarctica, right? There's most of the ice shelves are pretty dry. But for Greenland, I know that there are, many previous work where people use the automated detection algorithms to identify both fractures and rivers. And in fact, many times it's hard to distinguish rivers from cracks for the case of Greenland. I think you often have to, after the automatic method, you have to manually separate the rivers from cracks. That's the case for Greenland.
Right.
But in this case, our resolution is so low, right? So it's lower than, so we just do that. The features we see are most likely related to the big crevasses formed at the base of ice shelves. So I think the river is ruled out from our Antarctic crack detection.
Okay, thanks.
And Ted has a question.
Hi. Yes. Hi. Great talk. Really liked it. but using MOAA for detecting surface crevasses is a bit of a problem. I think most of what you saw in your mapping are actually bottom crevasses with a surface expression, and only a few of those. You are showing a great case here with Thwaites Glacier, but only a few of those will actually break through to the surface, and it would change the dynamics that you're calculating with your approach. If it's already mostly cracked from underneath before the water starts to accumulate on top and find a flaw near the surface. I think a better method for extracting the damage map for Antarctica would be looking at SAR mapping to look at brighter areas that are scattering the radar more strongly because there's actual surface crevassing. And another way would be to use Landsat data and extract a surface roughness from that. Wouldn't be too hard to do. I'm trying to do that, but it's just, I like everything about it. It's just that the locations of where things are at risk from hydrofracture might be different if you used a more finely focused detector for the surface crevassing.
So Ted, I thank you for the comment. I completely agree. Our result is limited by the resolution, and I completely agree. If we increase the resolution, we might see a different, the location of cracks could look completely different. There is a team of there are several teams working on using Sentinel images with a similar UNet I was using to identify cracks in a higher resolution images. And it's actually quite exciting. I don't know if they're so they haven't. I think the current status is that they're I haven't seen people detecting cracks on Sentinel images and put it on this diagram. But I'll also be really, really interested to see how that affected whether that move, the points. So that's
this graphic also brings up another question, and we're touching upon it right now, that in some cases where your dots are plotting at a stress level that should be lower than the formation of a crack, a lot of crack formation in Antarctica advects downstream to areas that are not at the same stress level as where the crack was originally formed. And you can still see them, or they would still show up in your remote sensing detection. Not really a problem with what you're saying. I think I really liked your talk, but it's something to consider about some of these outlier points that you've identified.
Yeah, the advection is a very good point. So we did one experiment. We did one thing because this is MODIS, so we don't have, we just have this one time. So one thing we did is we take the velocity of the ice and then we put the fracture back in the location where it experienced the highest stress in its advection history. Does that make sense? So like I guess like we did that, and then
this diagram, or that's something you're working on?
So we did this as part of like it was in one of the figures in the supplementary material.
Okay.
But it was actually to address this concern that when fracture advect downstream, it can potentially experience higher stress at some point in its advection history. So what we did was we track it back to history and then identify the highest stress each fracture had experienced. And then what the plot looks like is that it shift the every fracture location slightly on this plot. So it's shifted towards the right because every fracture we report the highest stress it has experienced. But it's still, it's still within, it's still not, it doesn't really cross the unstable boundary. But I think that's a way to, answer this kind of advection question, assuming that the velocity is under steady state. Yeah. Which is, yeah.
most places, yeah.
But that can be applicable to the case when a higher resolution fracture map is available. I think that can also be done.
Yeah, interesting. Thank you.
Thanks. And so Jeff has another question.
I had a wider question, which was whether that plot you have up at the moment, whether you could determine whether long period swell would crack the ice shelf. So if we're losing sea ice quite rapidly around Antarctica in summer, there's going to be ice shelves which are exposed to open water. In fact, Larsen C was actually had no sea ice in front of it.
Yeah.
So it might be that long period swell from, say, the Indian Ocean might lead to enhanced calving.
Oh, absolutely. So you're saying that the loss, is it right that you're saying the loss of sea ice, how you're asking about how it can affect our analysis and affect crack?
Yes, because
That's a
sea
great
ice
question.
attenuates swell.
Yeah, I'm also working on that right now. So I think the easy I guess the sea ice is a completely also another world, right? Where the model is depend on how you model sea ice, but sea ice impose it modify the boundary conditions at the calving front. So there are, as you said, if you remove sea ice, and then the stresses imposed at the front of the calving front can change, and then that can change the stress within the ice shelf. And how does removing sea ice affect the crack propagation? That's a big question, right? Like we're working on how like one simple thing we are working on is by changing the boundary condition of the calving front. How does that affect the stress in the ice shelf? And then couple that with the framework I presented here. So to see like under what condition can you have fracture destabilizing effect based on reducing sea ice. But that work now is pretty much at a conceptual level, hasn't really applied that to the data we see.
Yes, okay, thanks.
Yeah, there were also some interesting work, recent work saying that if you have sea ice in a rift, right, it can affect the stability of the horizontally propagating rift as well. That's another different effect that sea ice can play on crack stability.
Okay, do we have any other questions? We're getting close to 12, so I guess we can stop there. So thanks again,
Yeah,
Yao.
thank you. Yeah, and if any follow-up questions, feel free to send me an email. Yeah, we're actively working on the crack detection now for higher resolution images. So, cool. Right. Okay. Thank you.